Hi, this is Graydon Cortez, and this is Lab 2, Motion of a Falling Object. So to start with, the purpose of this lab is to observe the motion of an object that is dropped from rest and falls somewhat slowly straight down and compare it to computational models based on physics principles. We'll be using Newton's second law of the momentum principle and also using force of gravity and also the force of gravity plus the drag force. Some important equations for this lab are the velocity update formula, Vf equals Vi plus F net over m times delta t, the position update formula, xf equals xi plus vx times delta t, and the drag force, the force of drag equals negative drag coefficient times the magnitude of velocity squared times v hat. So the main result of this lab is an object falling straight down from rest will be affected by both the force of gravity and drag force, meaning it falls at a non-constant velocity to begin with, reaches a terminal velocity, and eventually F net will be approximately equal to 0. This will be proven through a video demonstration as well as the computational models using code. The model's assumption and physics principles mentioned are used to prove that the momentum principle holds true and that it can be recreated in different settings, which is F net equals delta P over delta T. So to start with, the conditions are the system is a crumpled tissue paper ball and the surroundings are everything else. The initial conditions, which are the tissue paper ball starts at t equals 0 seconds, is the initial position of negative 0.001 meters, initial velocity of 0.000 meters per second. The mass of the object is approximately 0.01 kilograms. The force of gravity is negative 9.80 newtons. And the assumed drag coefficient for the coding part of this lab is 0.335. So to begin with, the experiment, I dropped a crumpled tissue paper ball from rest and took a video of it falling with non-constant velocity. And to the right are the results of the video experiment through analysis with the tracker software and a visual of the movement of the crumpled tissue paper ball. The coding part of this, only gravity. First, you take the initial velocity and position found via the experiment step, create a computational model via the following steps. You first divide the total time into smaller time steps, and then at each time step, while in a while loop, you compute the gravity force, which is the weight, compute the net force, and this part, F net, is the weight, update the velocity using the velocity update formula, update the position using the position update formula, and then update the time, which is just t plus delta t. And to the right, you can see the most important parts of the glow script, as well as the results of the glow script code with only gravity. So now for the next part, the coding with gravity and drag included. So you do the same thing in the beginning, but the difference in this part is that after you compute the gravity force, which is the weight, you also compute the drag force. That's shown in the code to the right. And after that, you compute the net force, which now that you have the drag force as well, you do F net equals the weight plus the drag force. And the results of this part of the experiment, or the coding, is shown to the right as well. So when comparing these two, the video analysis results from tracker and the computational model factoring in drag, the y position versus time points are nearly identical minus a few deviations. This indicates the coefficient of drag used is approximately accurate and the force of drag is acting on the system. And the difference between the models are the computational model utilizing only gravity provided very different results and deviated away from the other two models by a large margin. This indicates that the model is not accurate when only using gravity, meaning that F net cannot be found using only gravity. And to the right is the position versus time graph of the three results plotted against each other. So you have the tracker one in blue, gravity is in orange, and gravity and drag model is in gray. So some possible sources of error are the crumpled tissue paper ball is not perfectly round. It has some holes, some places where it's not perfectly round, meaning the velocity of it falling could be different under different circumstances. The drag coefficient is approximated, not calculated. Therefore, the computational model matching it with the real life events could be slightly off. And the crumpled tissue paper ball does not hit the ground in the video, thus meaning that the data points gathered in tracker cannot be representative of the true effect gravity and drag had on the crumpled tissue paper ball. Lastly, what if? So the gravity plus drag force computational model predicts a terminal velocity. After t equals 0.033 in the model, the terminal velocity becomes approximately negative 0.53 meters per second, as calculated in the glow script. This occurs because the net force is approximately 0 when the drag force and gravity forces go against each other. In other words, the constant velocity, which is the terminal velocity, means that F net equals 0 newtons. Secondly, if the object was initially thrown downward, then according to the testing I did in GlowScript, terminal velocity would be roughly the same value as the same object dropped from rest, but it would occur slightly after the object was dropped. This is most likely because the gravity and drag forces still cancel each other out, thus meaning eventually the velocity will enter into a terminal velocity. It'll be constant since F net would be 0, which means a constant velocity.